Hello and welcome back. Today we're going over section 3.2 on linear models. And we'll see how to use the calculators to build some models, build us some equations to make predictions based on data sets. So first, we'll look at a few examples of linear versus nonlinear models. So the idea is that we have a bunch of paired data. So not terribly different from the ordered pairs that we're using to graph equations. And let's say each of these dots represents another piece of data. So while I can't draw one line and hit every single one of those dots, that is definite, I would not be able to hit them all with one line. Overall, you can see a pattern. You can see that as you move from left to right, there's a definite pattern that the inputs and outputs are following. As your inputs are getting higher, your outputs are also getting higher. Whether the arrow is on one end or both end kind of depends on what type of inputs you have. For example, time typically would not be able to go back this way. So since this does have a linear appearance, even though we can't hit all of the points with one line, this is considered a linear relationship between the data. And we have different strengths of linear relationships. The more scattered they are from the line, the weaker the relationship, the correlation between the two variables, but it would still be considered a linear relationship. So if I can still just take one line and put it through the bulk of that data, that is still considered a linear model. And as opposed to if we see something along these lines where it looks almost like a parabola, this would be a common one for fuel consumption on the vertical and speed on the horizontal. Lower speed are using more fuel just because you're not traveling as far as quickly. We hit kind of best fuel efficiency somewhere down here, and then once we hit past that speed, the wind resistance starts using up more gas than the gains that we're making by driving faster. So not all models are linear. I couldn't draw one line through all of this to describe the relationship, so this one is nonlinear. I'll do maybe one more before we do our own sort of model on here. This is another common model that you will see, but definitely does not fall into the linear category. I can't put the ruler in one spot to describe what's happening with that data. This is following what would be called a logarithmic curve. We'll study logarithms later in the course. If any of you have ever taught or coached in kids sports leagues, an hour of their time practicing, they go from not knowing what to do with the ball. Do I use my hands, my feet? What do I use in this sport? Not knowing what the goal is. Am I shooting for a net of some kind? Basketball, am I shooting it through a basket? Volleyball, tennis, badminton, those. Do I want to get it over the net and onto the floor on the other side of the net, that kind of thing. 1 hour, they go from not knowing where to stand, what to do, what the purpose of the game is. They've got a pretty good idea of, okay, now I understand what this is all about. An hour for a kid early on that knows nothing about it, pretty sharp, dramatic improvement in just an hour. And every hour of practice, they kind of get better and better. Down here would be more the change in a professional athlete. Top tier basketball players, say someone in the NBA, 1 hour of practice with them, they're not a different player than they were before they started that hour of practice. They are improving. That's why they're still doing it, obviously. But it's a much more minuscule level of change when they're at that highest of a skill level. So this is another example where we are not linear in form. So next we'll take a look at doing a scatter plot and what's called a line of best fit. So let's say we're measuring males age 18 to 34, and we're looking at height in inches and the weight in pounds. Excuse me. And I'll just go ahead and fill out the chart. So subject number 1, 72 inches tall, 6 foot even, 200 pounds. Subject number 2, 70 inches tall, so 5'10", and 195 pounds for the weight, and so on. So subject number 3, 66 inches tall, 180 pounds, 78 inches tall, 260 pounds, 68 inches tall, 200 pounds, another 68-inch tall subject, this one 185 pounds. And I'll just sort of separate these every couple just to make it a little bit easier visually to read it. Let's see, 71 inches tall. That subject was also 185 pounds, 70 inches tall, 190 pounds. 64 inches tall, so 5'4", 150 pounds, and 69 inches tall, 170 pounds. So first I want to see, is this data linear or non-linear? Now I don't have access to my smartboard, so unfortunately this is going to be my smartboard. Notice all of the data was positive on both the input and output. So we're really only interested in Q1, so I'm not going to use my stamper that has quadrants 1, 2, 3, and 4. So we'll just kind of do this one in by hand. And as much room as I can on this guy. All right, so my input is the height, my output is the weight, in pounds for the weight, inches for the height. And then I have to decide how much to scale these by. Another common practice to let the reader know that you are in fact skipping some data. Or not skipping data, my apologies, or you're skipping some input values. If we're measuring adult males 18 to 34 years old, it doesn't make sense for me to show heights and weights for, say, 0 to 18 inches tall. There's no 18-year-old males that are 1.5 feet tall. So to tell the reader that I am skipping some values to get to my data, we have just this little excuse me, symbol that just lets the reader know we're skipping some values and getting to the good stuff, so to speak. So let's see, our shortest participant here was 64, tallest was 78. So maybe I'll start at 64 and count by twos. Okay, so then vertically, our lightest person was $150, heaviest was 260, so that's again quite a good range there. So we can scale that by, sorry for that, had to pause the video for just one moment. We'll scale that by maybe 10-pound increments. So 150, 160, 170, 180, 190, 200, 210, 220, 230, 240, 250, 260 is our top there. I could have spread them out a bit further, but this is sufficient to get our picture of the data. So as far as making a scatter plot, once you have your scales done, you're just plotting ordered pairs. So 72 is paired with 200. There, I'll bring my ruler along just to make it a little easier for me to track. Do it reasonably neatly. So there's our 200 mark. So there's my first dot. 70 inches tall, 195 pounds. So between 190 and 200, there's our second person. 66 inches tall and 180 pounds. $78 inches tall and 260 pounds. $68 inches tall, 200 pounds. $68 inches tall again, but 185 pounds. Uh, 71 inches tall and 185 pounds. 70 inches tall, 190 pounds. $64 inches tall, 150 pounds. And 69 inches tall, 170 pounds. So as you can see, we do have sort of a general linear relationship here. It's not forming a nice, neat, pretty, perfect line, but remember from these others, it's not going to form perfect relationships. Now, as far as how to describe that, that's where our calculator comes out to help us. Here we go. So you're going to go into your stats menu. So your stats menu is down here right below your delete key. First thing that will come up, you'll see the option of edit. We want to edit. We will hit delete on any of the old data pieces. If you have a large list, let's say I have, I'll just put some random things in here, lots and lots of items in list number 1, but I don't want to see them anymore. Instead of deleting one at a time, you can clear list one. You don't want to delete list one. Clear list number one, hit the down arrow, and it will get rid of the old data in there. So list one, that will be our input list by default. So that will be our heights. So I'll just key those in. So 72, hit enter, 70, hit enter, and so on. 66, 78, 68, 68 again, 71, 70, 64, and 69. L2, the outputs are quote-unquote Y values, and just key them in one at a time. The order does matter, remember, because they are each ordered pairs, so each one is corresponding to one person. So $180, 260, 200, 185, 190, 150, 170. And I missed one of my 185. So 200, 185, another 185, then a 190, then a 150, and finally a 170. So if I want to know the equation of the line that should go through these, we can have it do a little bit of calculation in the stats menu. So back to the stats, remember that's right below your delete key. Now that we've got our data in there, we're going to arrow over to this middle option of calculate, and we want a linear regression. That is option 4, AX plus B. Your stats class might do the linear regression as A plus BX form. Typically a math class would be AX plus B form. Just make sure you're paying attention to where your X goes. So option number 4, linear regression, AX plus B form, and hit enter. It'll think for a minute. It'll give you R and R squared. Those you can talk to your stats teacher about what those mean. We're not going to do anything with the R and R squared. We just need our line. And we'll round these to, let's say, the nearest hundredth for each. So then Y equals, you'll see in your stats class, sometimes they call it Y hat, AX plus B, so 6.78 times X plus B, so plus a negative 280.63, so minus 280.63, 63 hundredths. And if I want to plot that, all I need is 2 points, and I'll just pick 2 of these input points, plug them in, find the output points, plot those 2, connect them with a line. So I'll try to do towards the extremes. So I'll try out 64, and I'll try out 78. So I'm trying out the 64, and I'll just use the rounded version, 6.78 times 64 plus 280 minus 280. I was wondering why I was getting a predicted weight of 713 pounds. 153.92, much more reasonable. So 64, 153.92. So that's about here. I'm going to do this in a separate color from the other dots I've got on there. So the other end of the board there, I've got the 78 on the high end. So this was 153.92. Trying out the same thing with the 78. If you don't want to key all of that in again, just change your 64 to 78, second and entry. That will call up the last thing you typed, and just change your 64, key it over to a 78. You don't have to type the whole thing over. So that one we have an output of 248.84. So 78, 248, close to 250. So then I will connect those 2 new black dots, and that's the equation of my line of best fit. Now we can also be asked to make some predictions. So based on our data, we could be asked to predict the weight of an 18 to 34-year-old male with a height of 79 inches. So that is another important thing to do in stats. You do want to stay close to your data. So our data went all the way up from 64 to 78. So 79, 80 inches, that would be reasonable. You want to stay, again, pretty close in. So on that one, we're just using the equation that we got before, y equals 6 7/800 times our input of 79 minus 280 63/100. And the output will be our predicted height. So I'll just second and entry again. So second entry, and replace our 78 with a 79. Again, sometimes in stats you'll see the y hat. I'm not going to require that for this class. 255 62/100. So the predicted weight is 255 62/100 in pounds. One other important thing to note on these linear equations, they're given to us in slope-intercept form. For some of them, the y-intercept is meaningless. This would be one of those cases. A y-intercept on this of negative 280.63, if we were to take it literally on what each variable means, it would mean that an 18 to 34-year-old man with a height of 0 would weigh negative 280.63 pounds. So the y-intercepts are not necessarily always meaningful for anything other than plotting points. However, the slope is meaningful. We could be asked to interpret the slope. So our slope m was 6 7/800. If I want that to look like a fraction, we're always allowed to divide by 1. And remember, slope is change in y divided by change in x. So our x was measuring the height in inches. So for each positive, so increase, positive 1, so each increase of 1 inch in height, there is a predicted increase of 6.78 pounds in weight. So this isn't saying that every time you increase 1 inch in height, your weight will go up exactly this much. This is just saying on average for this data set, someone that's 1 inch taller will be about 6.78 pounds heavier. All right, so that should be enough to get you through the 3.2 problem. So I would recommend 1 through 10 all, 11 through 19 on the odds. And I'll try to make some equivalent ones in the my math lab for those of you trying it that way. If you have questions, get in touch with me. Otherwise, I'll see you next time. Thank you.